Hello, Sam Moore here again, working one more time on trying to explain the workings of your electric guitar to you without math. Okay, so that makes it a little tricky, but we're gonna get there. Guess what I got? I've got a tube here of a muscle analgesic, relaxes pain away. When you get all of this decorative platinum blonde hair like this, sometimes you have to use some stuff like that. But that's just a matter of the platinum blonde hair. Okay. Last week we started talking about the frequency spectrum and spectrum analyzers and how you can see the different frequency components of the output waveform. We talked about how the output waveform of your guitar, your electric guitar, was just a bunch of sine waves, all of differing frequencies and amplitudes, all added together to make one more complex waveform. We synthesized or made a square wave by just adding a bunch of sine waves together so that you could see how you can add sine waves together and get a completely different looking waveform than the one you started with. I did a frequency analysis on my acoustic guitar so you can see how there are tools out there that you can use to see exactly what frequencies are in that waveform and the amplitudes of those frequencies. I did not tell you last week, as I went back and watched the video or reviewed the video while posting it, who wrote the program that I used to do the frequency analysis or the spectrum analysis. That was not me. I did write the program that added the waveforms together to generate the sine wave, but the spectrum analyzer is called Audio Spectrum Analyzer, and it's by Black Cat Systems. It's available on the App Store. It's inexpensive. It's easy to use and kind of fun to play with. You know, you can get on there and see what the spectrum of your voice looks like versus the spectrum of your buddy's voice. Okay, since then I've done a couple different spectrums that we're going to look at here, and we'll use those different spectrums to further understand the output and what we're seeing from the spectrum analyzer. So give me a moment. Let's move the camera and get all set up for that. Okay, I've pulled up two spectrums here. One from my acoustic guitar that we pulled up and we looked at last week, and one from my electric guitar. Now you can see they're very different appearing. There's some reasons for that that we'll get into eventually. Now, across this axis, we've got frequency. This is 10 hertz or 10 cycles per second. This is 20 kilohertz or 20,000 cycles per second. So as we go across here, we can see the frequencies increase. 10 hertz, 20 hertz. I'm having a little trouble reading that. 50 hertz, 100 hertz, 200 hertz, 500 hertz. And we can see the amplitudes of the different frequencies that appear. But just know that these are comparisons of amplitudes. They're not exact numbers. Okay? But we can see here's 106 hertz right here, and the numbers are all kind of jumbled up and written on top of each other. Here's our electric guitar over here. You'll note, I should say, these are exactly the same chord here and here. You'll note the electric guitar has a lot more high frequency components, or a lot more high frequency portions of the waveforms. There are some reasons for that rooted in physics, and then maybe we'll get into that eventually, but not today. But for now, let's just say these are two spectrums: acoustic spectrum, electric spectrum, exactly the same chord. I took both guitars and tuned them both to pitch, and actually they're just open. I just strummed across the open strings here and just strummed across the open strings here of both guitars tuned to pitch. You'll note different spectrums. Everybody who's ever listened to an acoustic guitar and an electric guitar knows the electric guitar sounds different than the acoustic guitar. The part that's different is the electric guitar actually sounds higher pitched, even when playing the same chord. It has a higher pitch. Those differences in the sound, those components in the frequency spectrum, which are present in the output waveform, between here and here are what we refer to as tone. Even though they're both tuned to exactly the same frequency, they sound different because they have a different tone. They have a different output spectrum. Okay, that's all I'm going to say about tone and output spectrums at this point, other than you can see and you can hear the difference between the sound of the acoustic and the sound of the electric because of the different frequencies in the output spectrum. Now we're going to talk a little bit about circuit simulation. Why do we use circuit simulation? Well, in this series of videos, we're using circuit simulation to avoid having to do a bunch of math. But the industry, or the electrical engineering community, well, basically they use it for the same reason, to avoid having to do a bunch of math. Circuits are so large and so complex at this point that it would take months and months and months and weeks and weeks and weeks to calculate or to predict the change of one small component making one small change. So you want to make a change in a circuit and change the value of one resistor 10%. It can cost millions of dollars to make the first prototype circuit, the first little prototype integrated circuit, just to see the effect of changing that one value. So what has happened is they've developed tools. The most commonly used tool is called SPICE, which stands for Simulation Program for Integrated Circuit Engineering. Yeah, SPICE. It was developed at UC Berkeley, University of California, Berkeley. At one time they did have a good engineering school. Came out in 1973. That was before they went, all wooga wooga and decided that political science was the only thing that we're going to study. SPICE has been around so long and been used by so many companies and so many people that it has become pretty much the industry standard. It's the program that everyone uses. Some people use other programs that are not SPICE, but if you look under the hood, you look into the actual guts of the program, it's SPICE. It's just wrapped up in a different wrapper. When it was first introduced and when it was first used, you would model your circuit in SPICE with a so-called network list. And you would have just a list of statements in a text file that would read something like R1 space 1 space 2 space 3K, which meant resistor number 1 goes from node 1 to node 2 and has value of 3Ks. And then you'd have C1, 2, 0, 6 micro, which meant capacitor 1 went from node 2 to node 0. Every circuit has to have a node 0 or a ground connection, and it was 6 microfarads. V1 goes from node 1 to node 2, and it's 1 and 1K. And these were kind of obscure comments, and I mean, you'd have hundreds and hundreds and hundreds of these statements in a definition for a circuit. And they didn't tell you anything. Well, they did tell you. They completely and absolutely described the circuit. But you couldn't just look at it and get a gut feeling for it. Nowadays, SPICE has been has developed graphics preprocessors, which is a graphical user interface. Basically, you just draw the circuit, just draw it out, just put components up there, and then and then the circuit will go and it'll take that picture and it'll take the picture and it'll write the network list for you. You never see the network list; it's buried in a file that you can, but it's buried in a file that you never access. Turns out there's a free version. Yep, free. Won't cost you a dime, won't cost you a penny. All you have to do is go and download it and get it. It is called LT Spice. I like to use LT Spice 4. There's another free version that's LT Spice 7. LT Spice, the LT stands for Linear Technology. Those are the people who are providing the program to you free at no cost. Linear Technology are good people. They produce good stuff. They make good circuits. You can get it to run on a PC. You can get it to run on a Mac. Now, I put together a simple circuit here, and we're going to play with it for just a couple minutes, just to see the kind of stuff that you can do with it. But Anyway, let me move the camera back in and we'll talk about this simple circuit. I've got to move camera in so you can see it. Okay, here's our simple circuit. And you'll note it is super simple. It's just a voltage source called V1, a resistor, R1. You see it's a squiggly line right here. That's R1. Has a value of 1K. And then R2, another resistor. I've made the value of R2 a parameter, a number that we can change as we go through the simulations. Here's the statement that changes the value of R2. This is kind of like the pot that we talked about last time, or the potentiometer. How you can vary the resistance of the part that's below the wiper that moves up and down. SPICE does not have a model for a potentiometer or for a pot, so you have to do things kind of like this. But you can see R is a parameter. There's R. R is a list. First, it's going to run the simulation with R at equal 500. Then it's going to run it with it equal to 1K, 2K, 3K, 4K, 5K. But anyway, this just tells me that we're doing a transient analysis. If you're going to see an AC waveform, you have to do a transient analysis. And it goes from 0 to 5 milliseconds. Okay? And it picks its own steps, its own time steps. But again, here's our voltage waveform. Okay? It's 1 volt, right? No DC offset, 1 volt, and has a frequency of 1 kilohertz. Remember that kilo means 1,000. Kilo means 1,000. Milli means 1 over 1,000. So it's got a frequency of 1,000 cycles per second, and it's going to run for 5 milliseconds or for 5 complete seconds. Now I have to reach over here, and let's just point down here, and let's run. Now, it's run the simulation. Oh, I don't see anything. Of course not. I haven't told it what I want to see yet. I want to see the voltage right here on the top of this resistor, right there. I don't know if you can see that cursor or not, but you can see that big old fat finger. So I want to see that voltage. Boom, there it is. There's the voltage at that point. Okay? Now remember our list. First, R2 is equal to 500 ohms. That's this lowest curve right here. I don't know if you can see the colors. That's the lowest curve. Okay? If we make R2 a little bit bigger, 1K, then you see the blue. I can barely see the blue, so I doubt that you can see it. 2K, now you got the red curve up here. 3K, I'm a little colorblind, so I can't tell you what color it is, but it's some color. They're varying colors as you go up and down through there. And you can see each of the different curves as it runs each transient. And that's just looking at the voltage at that point. Just like we talked about when we talked about potentiometers, as you turn that voltage up, okay, the voltage that appears across it is going to get bigger. Bigger resistance, bigger voltage. Okay, let's stop there for a moment. Get my smiling face back on. Next week, we're going to start talking about capacitors. And like I said, everything we've done to this point is so that I can make statements about capacitors and say things about capacitors, and you'll understand what I'm saying. When I say frequency, you'll know I mean wiggles per second. When I say period, you'll know I mean how long it takes one wiggle to take. When I say amplitude, you'll know I'm talking about how big the circuit is. And we've talked a little bit about tone. We'll do more about tone later on, and I'll put my boots on, step on some toes there, so you might as well start getting ready for it. Until then, keep on picking.